Hey guys, I hope you're all doing good. In this video, we are going to be writing a program to solve the forward kinematics of a 2-hour robotic arm manipulator. So robotics is an emerging field, and as mechanical engineers, learning how to write simple programs to simulate robotic arms is a good skill set to have. When you get started with robotics, the first thing that you learn is the kinematics of the linkages. If you're able to understand the kinematics, then you can write simple programs that simulate how the robot is going to move. This has a lot of applications. If you are able to figure out how the robot is going to move, then you can figure out its workspace. The workspace refers to the possible locations that the robot can reach. This is very important when people are designing robots for really complex applications such as welding a complex frame. So to get started, we are going to be looking at a 2-hour robotic arm. So first I'm going to draw the base of the robot, and a 2-hour robotic arm contains 2 links and 2 rotational joints. This right here is the first link, and this right here is the second link. So the link 1 is going to make an angle of theta 1 with respect to the x-axis, and the link 2 is going to make an angle of theta 2 with respect to the x-axis. So let us say the length of link 1 is L1 and the length of link 2 is L2. So with respect to forward kinematics, the problem reduces to the following. If theta 1 and theta 2 are given, what is the final position of the manipulator? So depending upon the application, the manipulator can be a welding tool or it can be a machining tool. So this problem is also called as the forward kinematics. So how are we going to solve the problem? The first step is to calculate the position of link 1. Okay, so how do we do that? So the link 1 has 2 endpoints, the starting point and the end point. The starting point is fixed to the base of the robot, and the ending point is connected to link 2. So the coordinate of the starting point is going to be 0, 0, and the coordinate of the end point of the first link is going to be L cos theta and L sin theta, where theta is going to be equal to theta 1. So the second step is to calculate the position of the second link. And to do this, I'm going to draw the link 2 separately. And we are going to represent link 1 using this imaginary line. Note that the end point of link 1 is the starting point of link 2, and we are going to assign a coordinate of x1, y1 to this particular point. And let us assign the coordinates x2, y2 to the end manipulator. So now x2 is going to be x1 plus L2 cos theta, and y2 is going to be y1 plus L2 sin theta, where theta is going to be theta 2. So far we have determined the coordinates of 3 points: the origin point, the end point of the first link, or also the starting point of the second link, and finally the end point of link number 2. With these 3 coordinates, I will be able to plot the 2 links, and when I write a program, I can do the required animation and determine the workspace. So now we are going to get started with the programming part. Alright guys, so let us begin the Matlab program. So to start with, I'm going to type in a comment to explain what the program does. And then we are going to get started with clear all, close all, and CLC. And we're going to be defining some inputs. So L1 is going to be the length of the first link, and let us say it's going to be equal to 1 meter. L2 is the length of the second link, which I'm going to say is 0.5 meters. You can experiment with the values. Then what we need to do is we need to have theta 1 and theta 2, right? So theta 1, let us say, is going to be equal to 45 degrees. And theta 2, let us say, is going to be 30 degrees. All right, and I'm just commenting it out. Now as far as my coordinates are concerned, I have 3 coordinates. So x0 is going to be 0 and y0 is going to be the 0. So this is the starting point of link number 1, which is the base of the robot, and that's going to be fixed. And x1 is going to be equal to L1 times cos d of theta 1. Alright, so notice that I'm using cos d instead of cos. So what's the difference? If I type in cos of 90, you will see that it is not 0, because cos function expects inputs in radians and cos d expects inputs in degrees. So in this case, since theta is specified in degrees, I need to be using cos d. and y2 is going to be L1 times sine d of theta 1, right? Okay, looks like I made a typo there, and let's use semicolon. Cool. What else is there? The final thing we need to do is determine the endpoint of link number 2, which I can call it as x2 and y2. So I made a typo here, so this should be y1. So let us say x2 is equal to x1 plus L2 times cos d of theta 1 or theta 2, sorry, and y2 is going to be y1 plus L2 times sine d of theta 2. Okay, I think I did that correctly. Alright, so now if I execute the program, you can see that x1, x2, y1, y2 have all been computed. Alright, so all I need to do now is just make a plot to visualize the links. And since I have 3 points, I can draw lines between them to visualize the robotic arm. So the way the line command works is quite simple. So it starts with line, and then you need to first provide the x coordinates of the 2 points that make up the line. So if you take link 1, the first point is the origin and second point is x1, y1, right? So what is going to be the list of x coordinates? It's going to be x0 and x1, correct? Followed by the list of y coordinates, which is y0, y1, or you can just use a space. And then we're going to use a line width parameter to say that we want a thicker line, and I'm going to use a line width of 3. And we are going to color this line using blue color. So this should do it. So if I execute this program, you will see that I'm getting a blue line which represents the first link. Alright, cool. So now what we want to do is we can just copy this and paste it again. And for the second link, I need to type in x1, x2 as the set of x coordinates, and y1 and y2 as the list of second coordinates, and we're going to be using red color. So if I plot this now, you can see that I'm getting 2 links. You can see that the second link is shorter than the first link. That's because L2 is 0.5. And you can see that this angle, the angle that your link 2 makes with respect to x-axis, is lesser than what the link 1 makes, because theta 1 is 45 and theta 2 is 90. You can just play with this. If theta 2 is 0, then your second link is going to be flat, right? And you can visualize that. And if you can make it 90, it's going to be straight. So that is a very simple forward kinematic simulator. Alright, but this plot looks a bit boring. So what I'm going to do is I'm going to make it a little bit more interesting. Basically what I'm trying to do is animate the plot so that it looks something like this. Alright, you can see that for each value of theta 1 and theta 2, the robotic arm takes a different position and we are animating it. How are we going to do this? So to do that, let's create a new file. Okay. The objective here is to have multiple values of theta 1 and theta 2, and for each value of theta 1 and theta 2 we are going to be creating the plot, and we are going to be stitching all those plots together to make an animation. So to start with, usual clear all, close all, and CLC, and inputs we are going to be using the same thing. This time theta 1 is going to be an array which I represent using the linspace command, linspace of 0, 90 degrees with 10 values in between them, and for theta 2 I can just copy the same line of code. Right, so theta 1 and theta 2 are going to have 10 values between 0 and 90. So if you do not know what linspace command is, say linspace of 1, 5, 10, right? So between 1 and 5 it's going to create 10 numbers, and let me just assign it to a variable called a, right? And a is a matrix, and if you type in size of a, you can determine the number of rows and number of columns in that matrix, which is 1 row and 10 columns. Alright, so I've done that. So let me put semicolon here. We have to define L1 and L2 as well. L1 and L2 are going to be fixed for a given problem. So L1 is 1 meter and L2 is going to be 0.5 meter. We are sticking with the same value. Okay, so what is the logic that we are going to use? You can see that we have multiple values of theta, right? In this case 10 values, and for each values of theta 1 and theta 2 we need to repeat this calculation, right? So previously when I typed this program, you noticed that I changed the value for theta 1 and theta 2 manually, right? The plot did change. Now we have to change the values for theta 1 and theta 2 using programming. And for that, we are going to be using the concept of a for loop. So what does for loop do? So for I equal to 1 is to length of theta 1, right? I'm going to print theta 1 of I. Okay, and let us save this program, run it, and see what it does. I'm going to be calling it as forward kinematics with for loop. Alright, so if I execute the program, you can see that the value of theta 2 is getting printed. Okay, so you will notice that I'm providing theta 1 here and theta 2 here, and that might be confusing for some people. So first of all, let us figure out what we are doing here. I'm saying that for I is equal to 1 to length of theta 1. What's going on there? So length of theta 1 basically refers to the number of values in theta 1. So if I type in length of theta 1, I'm going to get a value of 10 there, which means that there are 10 values, and your value of I is going to change from 1 to length of theta 1, which is 10. So if I type in something like I equal to 1 is to 10, you can see that the value of I changes from 1 to 10. Now when I execute it as it is, this is a matrix, right? So if I type in size of I, it's 1 row and 10 columns. However, when I use this in a for loop, that means the value of I is going to change from 1 to 10. Each and every time it's just going to store only one value. It's not going to be an array, it's a single value, but its value is going to change from 1 to 10. And each time the value changes, it's going to execute the set of commands that are present inside the for loop. So if I type in disp hello, alright, and if I delete this line, what's going to happen is it's going to display the word hello 10 times. Now it doesn't matter if I use theta 1 or theta 2, right? It's going to give me the same output because theta 1 and theta 2 contain 10 values. Okay, I hope that makes sense. So here what I can also do is I can just say that A is equal to strcat of hello, comma num to string of I. Alright, this might be a bit confusing for you, but let me just explain to you what I'm trying to do here. I'm going to print the word hello followed by the number I. Okay, if I execute this, you can see that my answer is continuously changing: hello 1, hello 2, hello 3, hello 4, and hello 5. So that is what for loop does. So here I'm saying that I is 1 to length of theta 2, and I in a for loop is called as a loop counter. It determines how many times the for loop is going to get executed. All right. So now what I'm going to do is I'm going to say theta 1 is equal to theta 1 of I. All right. And theta 2 is equal to theta 2 of I. So what I'm trying to do here is, as the value of I changes, I'm taking theta 1 and theta 2 from the original arrays, and I'm assigning it to a variable called theta 1 and theta 2 where it's capitalized. Now capital theta 1 or uppercase theta 1 is a variable. It's not an array. It contains only one value, right? On the other hand, theta 1 lowercase contains 10 values, and we need to use the loop counter variable here to access the particular value. So when I is equal to 1, we take the first value of theta, and when I equal to 2, we take the second value of theta. Alright, so the logic here is we use the value of I to take a particular value for theta 1 and theta 2, and then what we are going to do is we are going to perform the forward kinematics calculations. Now there is a key difference here. Now for each value of theta 1, which is basically for each position of link 1, link 2 can take multiple positions. What does that position depend on? It depends on theta 2. So in other words, if this is theta 1, theta 2 needs to be varied using another for loop. And we are going to say for j equal to 1 to length of theta 2. And for consistency, I can change this to theta 1 and have this as theta 2. And type in end, and this needs to be j. make sure that for each for loop, the loop counter variable is different. If I use I instead of j here, then things are going to be wrong. So let us think about what we are trying to do here. For each value of theta 1, we are looping through the value of theta 2. In other words, if I print hello inside this loop, can you guess how many times it's going to get printed? You can pause this video and try to guess it. Alright, so let us execute it. You can see that it's getting printed 100 times because theta 1 has 10 values and theta 2 has 10 values, so the total combination is 100, 10 times 10. Okay, so I need to perform my forward kinematics calculations here. So what I can do is I can just go here, copy all this code. The major thing that I need to change is that this should be theta 1 and this should be theta 2. So before I make the plot, I'll correct a small mistake. This needs to be theta 2 of j, right? Because theta 2 is controlled by the second for loop. And if I execute the program, you can see that I'm getting this crazy plot. So for each value of theta 1, I'm changing theta 2 and my link changes differently. Now visualizing this all in the same plot looks a bit funny. What I'm going to do is I'm going to type in figure of counter. And what is counter going to be? Well, let us say that counter is going to start with 1, and each and every time the for loop is getting executed, I'm going to say that counter is equal to counter plus 1. I'm incrementing it. Now for demonstration purposes, I'm going to reduce the number of plots. So I can do this by decreasing theta 1 and theta 2 to 4. And if I execute it now, you can see that I have 16 plots in total. Each plot basically represents a particular combination of theta 1 and theta 2, right? So it represents how the robot occupies different positions. Now clearly this is not a very good way to represent the plot. So what do we do next? Okay, so the first thing I'm going to do is convert this line command to a plot command. And if I execute the program now, you will see that I'm getting 16 figures just like previously, but I'm just seeing only one link. I'm just seeing the second link. That is because when you're using the plot command, the most recent plot command is displayed. To prevent this from happening, I can use hold on so that the plots do not get overwritten. So if I type in hold on and if I execute this, I should get very similar plots as before. All right. However, the advantage of using a plot command is I can actually remove this, and what I can do is I can say pause of 0.3. And if I execute the program now, you can see that for each value of theta 1, you can see how theta 2 changes, and you can visualize the problem a little bit more. But even this is still not enough. The plot still looks ugly. So what I can do is I can just delete my second plot statement and just have a single plot statement where I have x0, x1, y0, y1, and similarly x1, x2, y1, y2, and I'm going to say the line width is 3. What's the difference here? Well, let me first execute this. When you execute this, you are kind of getting the same thing. Now the problem that's happening is you are getting different colors for each and every link, and the color is being changed randomly. That we can fix it, not a problem. If I close all and if I remove the hold on command now, and if I type in F5, you will see an animation, right? You can see that for each value of theta 1, how theta 2 changes. And to make this a bit more clear, what I'm going to do is I'm going to fix my axis. I'm going to say that axis, when I say axis, I'm going to change my x limits and y limits. I'm going to say that my x limit changes from -1 to 1, and y limit say changes from 0 to 1.5. So something like this. If I execute the code now, oops, I forgot a bracket. If I execute the code now, right, you can visualize the robotic arm a little bit more. All right, you can see what it's doing. And maybe what I should do is I should just change this to 0.1 and maybe this to 1.5. And if I execute the program now, okay, so that looks good. What else can I do? I can change the pause interval to 0.03. Okay, that was a bit fast, so maybe we should just go with 0.1. All right, and to make it a bit more interesting, we can increase the resolution for theta1 and theta2. So now this looks more like an animation. For each value of theta1, you can see the theta2 is getting changed. You can think of this as your robotic arm, and if you are closely monitoring the end effector or the manipulator, if you are tracing it completely, then that is going to be your workspace. So let me Control C here and change this guy to 0.03. And if I play this now, the animation is much more smoother and you can see what's going on. Alright, so now we know how to create an animation on the screen. However, this is not a very elegant solution because we are pausing the code. The pause command basically pauses the code, which is not very efficient. So how do we create a movie from this particular example? Okay, so that is what we are going to be looking at next. So the first thing we need to do is get individual frames, and we are going to save that in an array called as m of ct, because ct represents each and every frame. And I'm going to use the get frame command. And what is the frame that I'm getting? I'm going to get the current figure window, right? So in this particular case, whenever a plot is made, it appears in a figure, right? You will see that the plot's title is figure 1, right? That is the figure window. We are going to get that particular figure window and we are going to save it in an array called as m. All right. And at the end of the for loop, if I type in movie of m, Matlab is going to generate a movie with all those frames. Okay. So then what we need to do is we need to create a new AVI file where we dump out all these frames. So I'm going to create a video file using the command video writer. And we need to give the file name and also the profile. The file name is going to be forward kinematics.avi, and we are going to be using uncompressed AVI. So once we have created this file, we are going to first open it, typing in video file, and then we are going to write to this video file. And what are we going to write? We are going to write the frames that we captured, and then we are going to finally close the video file. Okay, so the operation failed a couple of times and I found out what the mistake was. I need to make sure that I'm saving the frames and only then should I increment my counter, right? Because what's happening is the value of CT is initially set to 2, right? Because I incremented it before I saved the first frame, and that was giving some problems. So also I'm going to reduce the number of frames to maybe 10 so that I can demonstrate this quite easily. The other thing that I want to fix is this should be called as write video. Okay, so now if I execute the program, it's going to show the animation and it's going to play the movie for me, and that's it. So now if I go to the location where the movie was saved, I can just play this using VLC, for example, and I can see my animation. So that's how you would simulate the forward kinematics of a simple 2-hour robotic arm manipulator. Alright, I'll see you guys in the next video. Bye.